And then we would call these dashes our chemical bonds. Chemical bonds, right? Chemical bonds can be covalent chemical bonds, ionic chemical bonds, okay, but they're the thing that keeps the atoms together in the repeating unit. Well, and we're going to actually remind you how this works. Water, if it's in its liquid state, I'm going to be careful because I'm going to go ahead and there's some polarity to water. Let's just go ahead and do it this way. Oxygens, are they partially negative or partially positive? Negative, yep. Partially negative, partially positive, partially positive, partially positive, partially positive, partially negative. I'm not going to do it for all of them. But actually this dot, 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 dot between the molecules, that is what we call an intermolecular, just like an interstate, intermolecular bond. Intermolecular bond. Okay? And the way it works, if something is in its liquid state, we said that there is a moderate degree of intermolecular bonding. Actually, intermolecular bonds is something we have already talked about earlier in Chem 1. I'm going to go ahead and try to be careful, though, and I'm going to connect the region of negativeness with the region of positiveness to their fellow water molecules. Okay? So intermolecular bonds. It's a player. Intermolecular bonds is why things aren't all gases. Things that are gases have no intermolecular bonds. Liquids have an intermediate degree of intermolecular bonds. Solids have a high degree of intermolecular bonds. So what's the nature of those intermolecular bonds? That's actually what we're going to be talking about here. So intermolecular bonds, actually those would be those forces between ions and ions, although I would call it, between ions and ions, I usually ions and molecules, molecules and molecules, okay. Intermolecular, interionic bonds, forces. So here we have not a water molecule, but an HCl molecule. If you look up the electronegativity of the chloride ion, it's partially negative, hydrogen partially positive. So just like I have over here, with a fellow HCl molecule, it would look like this. Okay, where that dot, dot, dot is the intermolecular bond. I know it says intermolecular force, but you just have to go force or bond interchangeably. Intermolecular bond. Now this says weak, but it's weak relative to that solid line there, which is the chemical bond. Okay, actually that's pretty strong intermolecular. So again, this is kind of back in Chem 1. We talked about intermolecular bonds. We talked about the three physical phases of matter. We said that solids have a high degree or lots of intermolecular bonds. Gases, if they're behaving ideally according to the ideal gas law equation, have no intermolecular bonds. We're going to see that in one of my favorite videos coming up again. And liquids are kind of somewhere in between. So intermolecular bonds, be thinking of these dot, dot, dots between the molecules. Let's see if this plays for us to play. This is the one that's short. I think if you loop it. I don't think I can. Oh, there we go. So it's just amazing. All matter has motion. Okay? But what would you say about the motion of gas? Lots of motion. Yeah, it's faster. And just less motion here. Now one thing that motion does is it actually is an indicator of the amount of kinetic energy something has. The more motion it has, the faster it's moving, the more kinetic energy it has. So gases have a lot of kinetic energy, solids have a less amount of kinetic energy. Alright, so here's an OpenStax figure. We have solid, liquid, and gas. So, as the lines drawn in from left to right, we're increasing kinetic energy from left to right. And then down here, we're increasing IMF. What does IMF stand for in physics? Intermolecular forces, exactly. Intermolecular bonds, intermolecular forces, exactly. Bonds / forces. Cool. All right. So again, this is something we talked about in Chem 1, which is kind of fun. So you're like, oh yeah, we got this. It takes energy to break bonds. Now those could either be chemical bonds or they could be intermolecular bonds. And this kind of goes the whole, if we go, solid, liquid, gas, you can add energy. This is something we talked about in Chem 1. Of course, if you're changing phases, we call that latent heat. Okay? Latent heat. Anyway, as we add energy, we're breaking those bonds. Well, what happens as bonds are formed with regard to energy? You guys remember that? It's not added, it's subtracted, released, exactly. So energy is released here, exactly. So it takes energy to break bonds, and when bonds are formed, like they're formed, as I've written up there, going from a gas to a liquid bond, intermolecular bonds are formed. A liquid to a solid, intermolecular bonds are formed. Energy is released. Remember these latent heats, we use these delta H's? Oh my gosh, these enthalpies. They drive you nuts. Okay, if energy is being added, is it positive or negative? Is energy is being added? Are the enthalpy changes positive or negative? Yep, they are positive. Okay, if energy is being released, then the enthalpy changes are negative. Yep. Intermolecular bonds. Takes energy to break them, and when they're formed, energy is released. Again, it's something we talked about in Chem 1. And this is another video I think we saw in Chem 1. So I actually, don't say I never gave you anything, so I actually printed this off because I have a, and I'm going to give you something too. Here's the pollen video. Just in case. Here's what because these are all, there's 7 of them, I think.
Yeah.
And there's all different types of intermolecular bonds. And it just depends basically on the things that are being connected. So the top one is the strongest, and they get as you go down. So for instance, if you have a pair of ions that are going to be connected, the thing between them, I'm just positive that is an ionic chemical bond. But it's an interionic bond. It's strongest of all. Alternatively, you can have, and how do I say this? I think this will work for you. Anytime you see the word dipole, just think of something that's polar. Something that has a dipole is polar. So anytime you see something that says dipole, think of just a polar, something that's polar, a polar substance. Not a polar bear, but if you have something that's polar and you stick ions to it, you have an ion-dipole intermolecular bond. If you have 2 things that are polar, you have a dipole-dipole bond. I'm going to come back to hydrogen bonding. Hydrogen bonding, I'll do it this way. I'm going to take ordinary type and I'm going to draw, and I'm going to say special type. When we talk about hydrogen bonding here a little bit, we're going to say hydrogen bonding is a special type of dipole-dipole bond. Our next option there is if you have something that's nonpolar. If you have something that's nonpolar, in order to get it to form an intermolecular bond, you have to just kind of, what we say, induce a pole on it. So polar, something that's polar, and something that's nonpolar. That's all it is. Dipole, induced dipole must be something that's polar, something that's nonpolar. I always, when I get to this part, this subject, I think of women sometimes when it's, or people when it's time to give birth, but that process hasn't started. Sometimes they will induce labor. I was thinking that induced labor, we're actually inducing a pole on something that's nonpolar. Then our last option up here is induced dipole, induced dipole. So what do you think? Are these polar things? Yep, these are two nonpolar things you got to stick together by inducing a dipole on them. Okay, can we come talking about? Okay. There's 6. I said 7. There's only 6. So the things with asterisks can actually only occur in mixtures. Makes sense, right? Because ion dipole means you have to have something that's polar and an ion. So you have two different substances coming together, forming intermolecular bonds. Okay. Dipole, induced dipole, something that's polar, nonpolar, must be a mixture. Okay. So these things can happen in pure substances. Your ion-ion intermolecular forces, interionic forces, hydrogen bonding can happen in pure substances. Dipole-dipole intermolecular bonds, that means you have two polar substances. Induced dipole means you have two nonpolar substances. So they can be pure or a mixture. So let's take them one at a time. So dipole, I said anytime you see dipole, think polar. So you have two polar substances. This is an example of dipole-dipole. Actually, it's a special example of dipole-dipole called hydrogen bond. But just like I drew it here, we're going to see that the positive parts and the negative parts of opposite molecules come together. So here's a nice little video to kind of show you that. Oops. Several you just saw, HCl. The chlorine is partially negative and the hydrogen is partially positive. So that dot, dot, dot is your intermolecular bond. Now, hydrogen bonding is a special type of dipole-dipole intermolecular bonds, hydrogen bonding. The criteria are that you need to have if the hydrogen bonding is occurring in your pure substance, you basically need to have a nice fat region of electronegativity, which this is great, partially negative, and you need to have a small, electronegative thing that's partially positive. So water can hydrogen bond. The other examples, and they're all associated with hydrogen, is instead of oxygen, you have nitrogen. So I can have NH. Last but not least, I can have FH. In all of these, the oxygen, the nitrogen, and fluorine are partially negative, and the hydrogen is partially positive. What that does is just kind of set you up for a nice charge separation. Okay. Cool. So is hydrogen bonding stronger or weaker than ordinary dipole-dipole? That sheet I gave you. Stronger. Yep, it is stronger. Exactly. So this is actually kind of what I drew on the board over here, where you see the partially positive hydrogen of one associated with one molecule intermolecularly bonding with the partially negative oxygen of another molecule, and that is a hydrogen bond. This is going back to those kind of potentiometric maps where the red is carrying a partially negative and the blues are partially positive. Kind of a busy slide there, showing you lots of intermolecular bonds, hydrogen bonds. So what do you think? This is NH3. So do you think, is this a hydrogen bond or is it an ordinary dipole-dipole? The three possibilities for hydrogen bonding. I said OH, I said NH, and I said FH. Definitely, it's hydrogen bonding. Yep. It doesn't matter how many H's there are. Yep. We're kind of isolating it. In fact, that's a good point because this NH could be on something more complicated. You know, we're going to kind of take this and we could add stuff over here and it could still hydrogen bond. It's a good point.
Can I ask you a question? So if we see, like you said, like O, the M, or the F with the H, we don't have to go through figuring it out. It's just automatically hydrogen bond.
It can hydrogen bond, yes.
Okay.
Yep. And sometimes you need to kind of see these on a Lewis structure or something, or somebody needs to tell you that it's there. Okay. Yep. So there is ammonia. So what do you think? Hydrogen bonding or ordinary dipole-dipole? Hydrogen bonding again. Yep. Makes that shape. Can't remember. Sometimes in general chemistry too, we do a chromatography experiment or two kind of throughout. All chromatography is, and you're going to see it done here. This is chromatography. This is a piece of paper, and the line or whatever is wicking up the paper. What makes it chromatography is we call the piece of paper, we'll call the stationary phase, and the wicking up that's what we'll call the mobile phase. Now, as it does that, there's an interaction between the liquid and the solid, and the interactions, how do I say, will go according to these intermolecular bonds we're talking about. This is a very busy slide. I was kind of surprised that OpenStax brings it in. It looks like this. You're like, what the heck? Can you see the wicking? Okay, this is the upward movement. Now, it looks kind of ghost-like back there. But what I see, can you see this look at water? Okay, there's the water. And then you can kind of see, I think this might be alcohol. But I know this big structure here is cellulose. I'll draw around it. Cellulose is that big thing right here. See how big that is? And these are your small, I think that might be alcohol, water, headed up. There's another cellulose. Cellulose, is that cellulose? Is that our stationary or mobile phase? Stationary. So in the cellulose, notice that it's got regions of negativeness and regions of positiveness within the cellulose, and that just kind of helps the stuff kind of migrate up, helps it wake up. Again, kind of a busy slide to talk about intermolecular bonds. These are just kind of temporary. They give it a leg up. It's kind of like a climber's looking for those little peg things. I can do it on my Wii Fit. Here's another video talking about strength with regard to intermolecular bonds. Actually, I can just kind of use this electronegativity thing. What's that?
It's all in one column.
It's all in one column. Yep, it's all in one column. These guys. So we're not doing the PO, but. So these are what we call analogous compounds, where we have H2TE, H2SE, H2S, and then H2O is way up there. Now, we would think H2O, like it said, is here, right? Now, you might be like, what in the heck does this have to do with intermolecular bonds? Well, does this make sense? What they're talking about is the boiling point temperature. So what they're saying is for S H2TE, you have to jack the temperature up way high in order for that to boil. What's the significance there? When you're boiling, you're breaking intermolecular bonds. Okay? So down here, they're saying the H2SE, you don't have to have as high a temperature. H2S, not as high a temperature again. We'll talk more about boiling point temperatures as an indication of intermolecular bonding. But can you see where it looks like this intermolecular bonding is wimpier than this, and this is wimpier than that? That's all it's saying. And so you would expect that H2O would be the wimpiest. Okay? But what is, well, we'll talk more about this. These guys, in order for intermolecular bonding to occur in a pure substance between the molecules of the same type, they're polar. So you have what's called what? Dipole-dipole intermolecular bond. Ordinary. Ordinary, ordinary, ordinary. But what's this one? Hydrogen bonding. Yeah. And it's just crazy. The strength of the hydrogen bond, that's what jacks up the boiling point temperature. We'll talk more, but I'll just briefly mention. So we kind of have a molecular weight trend going on here, don't we? The higher the molecular weight, the stronger the intermolecular bonding. Lower molecular weight, wimpier. Lower molecular weight, wimpier. And what we're going to see is that with the greater the size, you have this other thing called the degree of polarization. It's just more polarizable. You can get a better dipole for something that's big. Polarities on your ends. All right. Another video. I told you, it's movie day. For dipole in pure substances, we have induced dipole. Now, what did I say? What sort of substances? Are you talking polar or nonpolar? Nonpolar, yep. So in order for nonpolar stuff to stick together, you have to basically induce a charge separation even though there's not one there. That's what the induced part works. Now this is one thing in chemistry where I have to apologize. There are different things in science I have to apologize. This one is, there's so many words for this same phenomenon. So induced dipole also means London forces, and I think OpenStax uses dispersion forces a lot. So if you hear dispersion forces, you're talking about nonpolar regions connecting with other nonpolar regions. That's dispersion forces. Induced dipole, same thing. Too many synonyms. London forces. So here's how this works. It's quite possible you have molecules sticking together, intermolecular bonds formed, and you have actually more than one thing going on at a time. If they're polar, you're going to have dipole, but it's possible within that same kind of pair of molecules that are connecting up, you also have these dispersion forces going on. Okay, so they're extra little connectors. Okay, so dispersion forces in general are always there. The larger the molecule, just like we saw with tellurium, the larger the molecule, the H2TE, then the more this is going to kick in, which is kind of why we saw that trend with the group 6A elements. All right, so here's an example of that. What we saw, intermolecular bonds between something that is nonpolar. So it's a temporary polarity. And so this would be your induced dipole intermolecular bond. So there are 7 elements that are diatomic. That's the Hoffer nickel, remember? So of those 7 elements, bromine and iodine are diatomic. So again, if you have a Br2 molecule, if you're going to calculate the electronegativity difference, they're going to both have the same electronegativity. So delta chi is 0. No electronegativity difference makes it very nonpolar. So in order for, this is a liquid, actually bromine, and I don't know if bromine should be a solid, I don't know. But bromine and mercury are the two liquids. Now this looks like bromine, this looks like a little hazy right there. Bromine is Br2 liquid, and this is Br2 gas. So it's a liquid, but it would be like in what we call equilibrium with this gaseous state. And can you kind of see the purple haze here? Starts letter S. What do we call it when something like iodine goes from a solid to a gas? Sublimation. Yep. Okay. But remember, if something goes from a liquid to a gas or solid to a gas, you have this sort of thing going on where bonds are being broken. Okay? Those intermolecular bonds are being broken. All right, so polarizability. I think I mentioned that a minute ago when I said, to me, that's why, and I keep holding this one up, but that's why H2TE has a higher boiling point temperature than H2S. Okay, it's more polarizable. And polarizability is important for those dispersion forces, for those induced dipole. Remember, those mean the same thing. Dispersion forces, induced dipole. So polarizability will increase with the number of electrons, just like we saw it with the H2TE versus the H2SE versus the H2S. Okay, more electrons, more polarizable. Larger atoms, more polarizable. When we get into looking at compounds that are similar in nature, the heavier the compound, the larger the mole mass of the compound, the more polarizable in general it is. So a little bit about semantics. So van der Waals forces. It can go a couple of different ways. Van der Waals forces, our textbook uses this term to talk about anything that forces involving only molecules and not ions. So that takes out your ion. Other books use van der Waals forces just to kind of talk about those. It's another word for dispersion forces. Van der Waals forces. The induced dipole, where both things are nonpolar. So I just throw that out there. All right, so I've got four compounds up here. Diatomic fluorine, HCl, HBr, HI. Here's how much they weigh. This third column here is what is the net dipole moment. So which one's the most polar of these four?
HCl.
HCl, it's got the highest net dipole moment. Very good. And F2, nonpolar. Now, when it comes for each of these four to bond with itself in its pure substance sort of situation, okay, the nonpolar F2, notice that it's not going to have any dipole-dipole interaction. That makes sense. The only way F2 is going to stick with itself is with those temporary dispersion forces. Remember, a synonym for dispersion forces is induced dipole, Okay. Notice with the HCl, that was the most polar, and it has the highest amount of dipole intermolecular bonding. But a large degree of what's keeping HCl to another HCl molecule is still those dispersion forces, the induced dipole. And HBr, HI, again, polar substances. It has a net dipole moment. It's not zero, they're polar. But notice that only a fraction, the smallest one, the HI, is what connects another HI molecule to itself, or to another HI molecule, is the dipole-dipole. A lot of it is that dispersion forces. So over here, heat of vaporization, this goes back to the latent heat of vaporization. So we must be talking about this sort of thing, right? Latent heat of vaporization. And hopefully you see a trend there, delta H back. Hopefully you see a trend there with the latent heat vaporization of this guy, which is only held together with dispersion forces, should be pretty low. And it is. That works. Okay. This guy right here, this HCl, does HCl hydrogen bond? No. I had to double check. No hydrogen bond going on there. But notice that this has the, well, how come this one down here, why is HI, the heat of vaporization, higher than HBr? What do you think? What's that? See this guy? Why is it the highest of these three? This guy's polar. And with increasing heat of vaporization, you're having to put in more energy to break the bonds to make it go from a liquid to a gas.
It has a higher mass.
It has a higher mass, exactly. I would go to this second column right here. Yep, its higher mass makes it more polarizable, and so it's even though its net dipole moment is less, it's more polarizable. So, yep. Oh, this last one is what's the boiling point temperatures. And so I think we're seeing a pretty good trend in increasing heat of vaporization, increasing boiling point temperatures here. Okay, so the last slide, I've got an assortment of compounds down here. Argon, CO, HI, HBr, HCl, NH3, and H2O. And I've got a possibility of 3 different types of intermolecular bonds. The yellow and the blue, we'll pick on those since those are here for argon and carbon monoxide. The yellow is induced dipole, so that's what your dispersion force is, isn't it? That's the yellow. The blue is dipole, dipole. Now, I don't like this because, can you see where, should this have any dipole, argon? No, but there's 2 different colors of blue. See, this is this guy, this is net guy. That's your net forces of all of your different types of intermolecular bonds. And this is your dispersion forces, or induced dipole. I wish they didn't have 2 different blues. Okay? So, yep, we don't have any dipole, we don't have any dipole-induced dipole. Now this next set, we have HI, HBr, HCl. Any hydrogen bonding here? Nope. No hydrogen bonding. But we do have some dipole force, because these are polar, right? So you can get dipole. See, that's the dark blue, so this is right here. What about these guys? NH3 and H2O, what do they have in common? Hydrogen bonding, yep. And so when you look at their overall net intermolecular forces, notice that this first one, which is the dipole, is way high for H2O and moderately high for NH3. Okay. So now you're ready for part 2 homework. Any questions? So we'll just stop there. We see you out early.
Is there due deadline part 2?
They're always due the next time we meet. So.
Oh, okay.
Yeah. Yep.
Wednesday.
Wednesday. Yes.